imagine walking into a room that is just absolutely freezing. We're talking instant bone-chilling cold.
Oh, wow. Okay, setting the scene.
Yeah. So your breath plumes out in front of you, frost immediately starts forming on your eyelashes, and, your only real thought is how to get out of that room before hypothermia sets in. It is incredibly hostile.
Right. I mean, it's pure survival mode at that point. Your biology is violently rejecting the environment, and all your body's energy diverts to just, keeping your core from shutting down entirely.
Exactly. So you rush out of there, open another door, and you step into a second room. But this one is like walking into a blast furnace.
Oh, okay. Out of the frying pan, literally.
Yeah. The air is so heavy and superheated, it physically burns your lungs to breathe. Like the heat is radiating off the walls, and you feel like you're just baking alive. So again, you want out immediately.
Right. So you've gone from one lethal extreme to, well, another lethal extreme. In both of those cases, the environment is fundamentally incompatible with the complex chemical reactions that actually keep you alive.
But then you find a third door. You open it, and the room is it's perfect. The temperature is exactly right.
Just right.
Yeah, there's a gentle breeze. You don't need a heavy coat. You aren't sweating. You can actually sit down, unpack your bags, and exist. It's basically the classic Goldilocks story. Not too hot, not too cold, just right.
It's an analogy we've all heard since childhood, right?
Yeah.
But it actually takes on a profound new weight when we apply it to astrophysics.
How so?
Well, because while Goldilocks was just looking for a decent bowl of porridge, astronomers are looking up at this dark, mostly sterile universe, searching for that exact same equilibrium on a massive cosmic scale.
We are looking for entire worlds that fit that description.
Yeah.
Like the prime real estate where life actually has a fighting chance to start.
Precisely.
And that is exactly what this deep dive is all about. We are embarking on this journey across space and time to explore the habitable zone. But as we're going to find out today, the popular idea of this zone like just drawing a neat little circle around a star is completely wrong.
Oh, yeah, it's a massive oversimplification.
Yeah.
I mean, the deeper astrobiologists dig into the mechanics of planetary science, the more we realize that habitability is this complex, three-layered puzzle.
3 layers.
Yeah, it's not just a single ring. You have to survive this gauntlet of conditions across the stellar level, the planetary level, and even the sweeping scale of the galaxy itself.
So we're going to unpack all 3 of those layers today, plus a few wild exceptions. But before we start jumping from stars to galaxies, I feel like we need to establish the baseline.
That's a good idea.
When we say habitability, what are we actually looking for? Like, what is the golden ticket here?
Liquid water.
Oh.
That is the absolute foundational requirement. It's the universal solvent for life as we knew it.
Why water, though? I mean, we always hear about water, but why couldn't life exist in, say, I don't know, a sea of liquid methane or just out on dry, warm rock?
Well, it really comes down to chemistry and movement. If you want life, which is essentially just a series of incredibly complex, self-sustaining chemical reactions, you need molecules to be able to mix, interact, and combine.
Okay, so they need a medium to move around in.
Exactly.
Yeah.
If your environment is completely frozen solid, those molecules are locked in place. They can't mingle. The chemistry just stops.
And if it's too hot, like the blast furnace room.
If it's too hot and the water is steam, well, the molecules are highly energetic. They're bouncing around violently and dissipating. They won't form those delicate, complex structures required for biology, like, proteins or DNA.
So it's literally too chaotic.
Right. Liquid water is the perfect mediator. Its unique chemical structure, specifically its polarity, allows it to dissolve a massive variety of nutrients and chemicals, floating them around gently enough that they can bump into each other and form complex chains over billions of years.
So the entire mission today, whether we are talking about a star burning millions of miles away, or the core of a planet, or the center of our galaxy, is ultimately a search for the precise conditions that allow water to remain in that precious liquid state.
That's it exactly.
Yeah.
I mean, we aren't necessarily looking for advanced civilizations right off the bat. We are looking for the cradle, the place where it can start.
Okay, let's start with layer 1 then. The most famous requirement, and the one that usually makes headlines when a new telescope spots a planet, the stellar habitable zone.
Right, the Goldilocks zone.
Yeah. So if liquid water is the goal, the star is basically the campfire that keeps it melted.
The campfire is actually an excellent way to visualize the physics at play here. A star is essentially a massive, ongoing nuclear fusion reactor. It pumps out radiation in all directions.
And it gets colder the further away you stand.
Exactly. It's defined by the inverse square law of light. As you move away from the star, the radiation spreads out and gets weaker.
So the zone isn't some physical boundary like a giant asteroid belt. It's just the orbital band where the radiation is perfectly diluted.
Right. By its strict physical definition, the stellar habitable zone is the orbital region where an Earth-like planet with sufficient atmospheric pressure can maintain liquid water on its surface.
Okay.
Step too close, the radiation overpowers the planet, the water boils, and you get a runaway greenhouse effect. You're in the furnace room.
And if you step too far back,
The radiation is too weak, and the planet becomes a global ball of ice. You're in the freezing room.
it sounds like a pretty simple math equation, honestly. You just measure the star's heat, draw a circle at the right distance, and you found your property line.
Well, yeah, that would be true if all stars were exactly the same, but they aren't. And the type of star completely dictates where that property line is drawn, how wide it is, and crucially, whether life actually has time to develop.
Right. So let's start with our own sun as the reference point. It's a G-type star, right?
Yeah, a standard yellow dwarf. They are relatively stable, medium-hot stars. For a star like ours, the habitable zone sits roughly between 1.9 and 1.5 astronomical units.
And 1 astronomical unit, or AU, is the distance from the Earth to the sun.
Exactly. So we're sitting at exactly 1.0 AU, perfectly inside that zero point 0.9 to 1.5 band.
We are squarely in the middle.
Mhm.
But if you look up at the night sky, yellow dwarfs aren't the only game in town. There are wildly different sizes and temperatures of stars out there.
Oh, absolutely. They're categorized by a spectral classification system. Astronomers use the letters O, B, A, F, G, K, and M.
Okay, that's a lot of letters to keep track of. Let's break those down a bit. What happens if we orbit something much, much bigger than the sun, like the O or B stars?
Let's look at those, yeah. The blue giants.
Yeah.
If our sun is a modest campfire, an O-type star is a towering, roaring bonfire. I mean, they are incredibly massive and burn at blistering temperatures.
So if I'm standing near a massive bonfire, I obviously can't be at 1 AU. I'd be completely incinerated. I have to back way, way up to feel that same comfortable warmth.
You'd have to back up tremendously. The habitable zone for a blue giant is pushed incredibly far out into its solar system, and the band itself is much wider. You could easily fit multiple planets in there comfortably.
Honestly, that sounds like a pretty good deal. A wide habitable zone, lots of room for planets to orbit lazily and stay warm. What's the catch?
It does sound ideal, but there is a fatal flaw in the blue giant system. It's a basic concept in astrophysics. The more massive a star is, the harder its gravity squeezes its own core.
Okay, makes sense.
And the harder the core is squeezed, the faster it burns through its nuclear fuel. So a massive O-type star might only live for a few million, maybe a few 100 million years, before it completely runs out of fuel and explodes in a supernova.
Wait, just a few 100 million years? That seems like a blip on a cosmic scale.
It is a microscopic fraction of time. Remember, it took Earth billions of years to go from a cooling rock to harboring even complex life.
Right, single-celled organisms ruled this planet for an unimaginably long time before evolving into anything multicellular.
Exactly.
Oh.
So if our sun had been a blue giant, it would have detonated while Earth was still just a lifeless, bubbling chemical soup.
So the fire burns out before the soup even gets to simmer. That essentially rules out all the giant, beautiful blue stars for finding advanced life. The biological clock simply runs out too fast.
Which forces astrobiologists to look at the complete opposite end of the stellar spectrum. If the O and B types are the roaring bonfires, we need to talk about the M-type stars, the red dwarfs.
Red dwarfs, these are the tiny, faintly glowing embers, right?
Yes, they are incredibly small, very cool compared to our sun and dimly lit. But what makes red dwarfs arguably the most important subject in astrobiology right now is their sheer numbers.
Really? How many are there?
They make up roughly 75% of all the stars in the Milky Way galaxy.
75%. Okay, so if we're playing a numbers game, the vast majority of planets in the universe are orbiting these little red dwarfs.
By a massive landslide. And because they're so small, their gravity isn't crushing their cores like the blue giants. They burn their hydrogen fuel at an incredibly slow, miserly rate.
So they live a long time.
Oh, a red dwarf won't just live for a few 100 million years. It'll live for trillions of years.
Trillion. But wait, the universe itself is only about 14 billion years old.
Exactly. Meaning not a single red dwarf in the history of the universe has ever died of old age yet. They will absolutely outlast every other type of star in the cosmos.
Okay, hold on. If they offer trillions of years of stability, that sounds like the ultimate jackpot for evolution. Biology has infinite time to figure things out, make mistakes, adapt, and grow. Why aren't we focusing all our energy just on red dwarfs?
Well, because we have to go back to the campfire analogy. If your heat source is just a tiny, faintly glowing red ember, and you want to keep your water liquid, where do you have to park your planet?
You have to huddle right on top of it. Like you'd have to orbit incredibly close just to get a little bit of warmth.
You'd have to orbit closer to that red dwarf than Mercury orbits our sun. And that introduces a monumental problem. When you park a planet that close to a star, things get violently complicated.
Complicated how?
Astrobiologists call this the red dwarf catch-22. To get the warmth, you subject your planet to two brutal physical realities. The first is tidal locking.
Tidal locking, that has to do with gravity, right? Like how we only ever see one side of our moon from Earth.
It is the exact same mechanism. Gravity isn't uniform, it's a gradient. The side of a planet facing the star experiences a slightly stronger gravitational pull than the dark side facing away.
Okay, so it pulls harder on the front than the back.
Exactly. This difference physically stretches the planet, creating what we call a tidal bulge.
Wait, so the rock of the planet is actually being pulled slightly out of a perfect sphere shape.
Yes. And as the planet rotates on its axis, that bulge is constantly dragging against the rock and magma of the planet itself. It creates immense internal friction.
Like rubbing your hands together really fast.
Right. Over millions of years, that friction acts like a massive brake, slowing the planet's rotation down until it finally locks. At that point, the planet's rotation period perfectly matches its orbit.
Meaning one side of the planet permanently faces the star, and the other side is permanently staring out into the black void of deep space.
A world completely divided. On the day side, the sun never sets. It just sits in the exact same spot in the sky forever.
That sounds awful.
It is. The heat is relentless. Any oceans on that side would likely boil away entirely, leaving an irradiated, blistering desert.
And on the night side.
Eternal darkness. The temperatures plummet to hundreds of degrees below zero. It is a permanent ice age. In fact,